Have you ever stopped to think about how your phone, your laptop, and maybe your neighbor's smart toaster can all be on the same Wi-Fi, and it doesn't just turn into a chaotic mess? Well, today, we're going to pull back the curtain on the amazing tech that makes it all work. We're talking about OFDM and OFDMA.
Seriously, think about it. You've got all these devices just screaming for a piece of the internet at the exact same time. So how does it all just work? Well, it's not magic. It's actually an incredibly brilliant piece of engineering that brings some serious order to all that chaos.
So to really get this, we've got to start at the beginning, with the foundation. And that foundational technology is called OFDM.
Okay, orthogonal frequency division modulation. Yeah, I know, that is a mouthful. But the two words you really want to lock in on are highly efficient. At its core, OFDM is just a really smart way to send data. Imagine taking one big, fast river of information and splitting it into a whole bunch of smaller, slower streams. Each of those little streams gets its own tiny, dedicated lane on the highway, and we call those lanes subcarriers.
You know, before we had OFDM, the old way of doing things was something called frequency division multiplexing, or FDM for short. And look, it worked, but it had one really big problem. It was super wasteful.
And you can really see what I'm talking about right here. Just look at the difference. On the left, that's the old FDM method. See those gaps between the channels? Those are called guard bands. They're basically empty buffer zones to keep the signals from crashing into each other. But all that empty space, that's just wasted potential, wasted bandwidth. Now look at the right. That's OFDM. It just gets rid of those guard bands completely and packs the channels so tight that they're actually overlapping. It's just so much more efficient. Okay, so that leads to the obvious question, right? If you're cramming all those signals right on top of each other, how on earth do you avoid a total traffic jam of interference? Well, the answer is kind of like magic, but it's actually just really cool math. It's a principle called orthogonality. And this is the secret sauce that makes the whole system tech.
So what does orthogonal even mean? Put simply, it means that even though these signals are overlapping in frequency, they're designed in a way that they're basically invisible to each other. When your phone's receiver's listening for one specific signal, at that exact measurement point, all the other signals are mathematically at zero. They just don't exist from the receiver's point of view at that moment.
And this visual really helps it click. See how each wave has a peak? That's where the receiver actually reads the data. Now, the absolute genius of OFDM is that the peak of one wave is timed perfectly to hit the exact spot where all the other waves are crossing the zero line, what we call their null point. So when the receiver is looking at that one peak to get its data, every other channel is literally at zero. They're silent. No interference, no need for guard bands. It's just pure, brilliant efficiency.
All right, so OFDM is fantastic for sending one huge chunk of data really efficiently. But the real world is rarely about just one device, is it? It's you, your family, everyone in the coffee shop, all trying to get online at once. So the technology had to get even smarter.
And that's where OFDMA comes in. The MA at the end stands for multiple access, and that's exactly what it does. It takes that awesome core idea of OFDM and levels it up for a world full of multiple users who all want a slice of the Wi-Fi pie at the exact same time.
So here's the key difference. With plain old OFDM, one device gets all the subcarriers for a split second. But with OFDMA, the system becomes a smart traffic cop. It can divvy up all the lanes, saying, all right, user A, you take these subcarriers. User B, you get this other group. User C, this little block is for you. And it's all happening simultaneously.
This picture shows it perfectly. That whole grid represents all the available resources. Look at how it's carved up like a patchwork quilt. User A gets a piece, user B gets another differently shaped piece, and so on. They're sharing everything, both the frequency and the time, in this super dynamic way. This is why your Wi-Fi at a crowded airport or a stadium doesn't just completely collapse. Okay, so we've got the what and the why down, but what about the how? How does a device actually create this incredibly complex signal and send it out into the air? Let's pop the hood and take a look at the transmitter.
It all has to start somewhere, right? And it starts with the basic ones and zeros of whatever you're doing. Your email, your video stream, you name it. The transmitter's job is to transform that simple digital data into that really complex, multi-layered OFDM wave we've been talking about.
This diagram here, this is basically the blueprint for how it's done. Now, I know it might look a little technical, but just think of it as a recipe. It's a step-by-step process moving from left to right that takes simple data in one end and spits out a very sophisticated radio signal on the other. So let's break it down.
First, the ones and zeros get assigned to all those different subcarriers we mentioned. Then comes the magic step. There's this mathematical engine. It's called an inverse discrete Fourier transform that acts like the conductor of an orchestra. It takes all these separate little notes, the subcarriers, and combines them into one single complex piece of music, the final OFDM signal. And it does it in a way that guarantees they all have that special orthogonal property. Finally, another piece just lines them all up in a single file, ready to be broadcast out by the antenna.
Now, one thing to point out, the material we're looking at gives us this fantastic, detailed look at the transmitter, how the signal gets made. The receiver, on the other end, pretty much just runs this whole process backwards to decode it all. But we don't have a specific diagram for the receiver in our sources for this explainer.
So, let's bring it all home. Why should you care about any of this? Well, it's simple. Because of OFDM and OFDMA, we get way more bang for our buck from our radio waves. That's what high spectral efficiency means. It makes our connections more robust and less likely to get messed up by interference. And this is no exaggeration. It is the absolute foundation that 4G, 5G, and modern Wi-Fi are built on. And, crucially, it's what lets a single network juggle tons of different users at the same time without breaking a sweat.
And that kind of leads to a final thought, doesn't it? The whole history of wireless has been this constant push to get smarter about how we use the airwaves. We went from wasting space with guard bands to this beautiful, elegant system of overlapping waves. So with our hunger for data just going up and up and up, you have to wonder, what's the next brilliant idea for sharing this limited resource even better? That's the question driving the future of wireless. And that's your explainer for today.